Okay, now we get back to original topic, exponential and sinusoidal signal. Let's consider this kind of equations. Okay, there is some function, and we can take a derivative, the fx of dx, but the differentiation and the original function are equal, like that kind of conditions. Is there any function like this one? A function equals to its derivative. We would like to find out that one. So here is the definitions. Fx plus delta x minus fx divided by delta x, and we taking the delta x limit to 0. So let's assume that there is some function of this one, x. Let's assume this one. Then the fx plus delta x will be e to the x plus delta x. At here e is not given, but there is some number e, and we take the exponent as a x. So e power to the x, like that. So fx plus delta x is this one, and fx is this one, and delta x is that one. By taking limit delta x goes to the 0, then it becomes the fx. Then this satisfied. Okay, so we would like to find out the e from here. So we taking dividing e to the x, then this becomes the 1, and this one is e to the minus e to the delta x, and ex is division, like that. So from here we can build up the equation with respect to the e. Okay, e can be expressed in that way. At here delta x goes to the 0, so it means that e is the number satisfying this one. Limit delta x goes to the 0, and equation are given like that. 1 divided by delta x. Okay, this is the equations. We would like to find out e. So then what can we take in the delta x? For example, delta x is 0.1, then 1 plus 0.1 over 10. Actually this one. Okay, this is 2.59. A little smaller than 0.1, 0.01. Then the equation will be 1 plus 0.1 over is 100. Okay, this is 2.7048. We need a more accurate one, then we can try this one. Then this one is 1 plus 0.0001, and it's 1,000 times, power of 1,000. So this one is 2.7169. This is accurate enough, but we need, if we need more accurate one, we can take in another limit, this one. So in this case, this much. So this one is 2.18. So we can approximate that the e equals to 2.72 something. This will be enough accuracy. So this is called e. Okay. Then we can write the equation like this way. Fx, if fx is e to the x, then df of dx equals like this one. So its differentiation is the same as that one. This is very useful in many applications. Okay, one of them is Euler equation. Okay, let's look at here. Euler equation can be proved in several different ways. I would like to show you one of them. So here is some function of fx. Okay, fx is defined by e to the jx. J is complex number here. We already know what is the complex number here. And cosine x plus j sine x. So we define the function fx like that way. And then take the derivative. d of dx. Then how we can write down this one? So the differentiation will be given like the way: f prime of x equals to cosine x plus j sine x to the square. And we need to take the derivative this one first and multiply that one. So taking derivative this one with respect to x, constant j will come out. And this is the differentiation definition. As we know that the e to the x, by taking derivative, will be the same form of this one. So this result comes directly from this result. Okay, and cosine x plus j sine x. Okay, and minus e to the jx. We need to take derivative of this one. So this is minus sine x plus j cosine x. Okay, this is the result. If you see the this part, then e to jx is common factor, so that can be written like the way: j x and cosine x plus j sine x square is common factor. The remainder looks like this one: j times cosine x, and j and j will be minus sine x, and from here minus will be plus, and minus and plus that will be minus. Okay, now you see here j cosine x minus j cosine x minus sine x is 0. This is 0. So you need to understand that f prime is 0, then it means this is constant. It doesn't change. Okay, this is constant. Then we can calculate f of 0. F of 0 means that the exponent 0, any number 0 is equals to 1. As we see here, any number 0 is always 1. It is just a division. Okay, so e to the 0 is 1. Okay, and the cosine x, if x is 0, then this is 1, and sine is 0. So that it means that it's 1. Therefore, f of x is 1, means that e to the j x and cosine x plus j sine x. This means that okay. From this result, we can write down the e to the jx equals to cosine x plus j sine x. So this is called Euler equations. So we proved this one by defining a f of x like this way, and by taking derivative, we know that this one is constant. And if we insert x equals to 0, then it was 1. That means the constant value is 1. Okay, then we can write e to the jx equals to cosine x plus j sine x. That's the one. The another the one is this one. If we take the Taylor series expansion for the e to the x is given like that, And the Taylor series is defined like this one. In case of e to the jx is expanded in that way, if you separated the real part and the imaginary part, then you can two different polynomials are given like that. This one is definition of the cosine x, and this one is a sine x, real part, real and imaginary part. So from the Euler equations, the complex exponent interpreted as a cosine and sine. So I talk about that the exponential and sinusoidal signal, it's the same things. If take the complex exponent, that becomes the sinusoidal signals. Okay, and to interpret this one, e to the jx can be interpreted in this way. This is a theta, then e to the j theta is this one. The real part is cosine theta, so it means that the the real part is cosine theta. This is cosine theta, and the imaginary part is a sine theta, j sine theta. Okay, so the complex exponent e to the j theta is just this angle. The magnitude is 1 at this moment. The magnitude is this length is 1. So this is unit circle. Okay, so we can write this one, e to the j theta equals to magnitude is 1, angle is a theta. So geometrically this point. Okay, by use of this one, we can express the another one. If length is r, angle is theta, then it can be written in this way. So the x-axis value r times cosine theta is the x component, and the imaginary component is r times sine theta. Okay, r sine theta is the imaginary component. So we can answer for this one. Y equal root j. What is this one? J is J equals to, you can express that one into this way. Magnitude is 1, angle is pi over 2. Okay, this is it. In this case, square root j is magnitude is 1 and angle is pi of 4. It means that this can be written in this way: e to the j pi over 2, like that. Then we can write this one, e to the j pi over 2. Then this will become e to the j pi over 4. So this is cosine pi over 4 plus j sine pi over 4. Okay, this one is square root 2 1 plus j. This is the result. But what if we taking the j as this way, 1 angle this way, pi over 2 plus 2 pi. In this case, we have different result will be given. Okay, in this case, the j equals to j pi over 2 plus j angle is pi over 2 plus 2 pi. Okay, then square root j is e to the j pi over 4 plus pi. Then you can interpret this one e to the j pi and e to the j pi over 4 minus 1 plus j and the square root of 2. You can get this result. So which one is correct? This is correct. The reason is this one. When we take the angle should be confined in the one period only. I mean that mathematically both are okay, but in the engineering terms, engineering point of view, we always confine the angle pi theta pi, or sometimes we can confine that one theta less than 2 pi. Okay, we conventionally using these reasons. When you studying the Fourier transform, this becomes the Nyquist zone, and sometimes you can taking this one is okay, but this is not allowed. Okay, so this is not the conventional value, so you need to think about this is not the correct. Okay, this is not correct one. Okay, we do not allow this kind of angle. Okay, we talk about y equals square root over j, so that is given in this way, and the conventional angle reason are given in this way. Then you can get this result, not this one. And what about this one, y equals e to the j? So what will be the value of this one? Think about that. You can find out the number by use of Python or Excel. Here shows one of the example here. To find out the square root j, I would like to import numpy and np dot SQLT 1j. Okay, this is complex number. I said that it's the square root 2 over 1 plus j, so it gives this one. So this one is 1 over square root 2, this is 1 over square root 2. Real and image part are the same because this one is cosine pi over 4. Okay, sorry, it's np dot cosine pi of 4, that's the 0.707. 0.707. Sine is also the same, pi over 4, the same thing. So that's why square root 1j looks like this one. What about this one? You need to think about, but the calculation is quite simple. You can do this one, power 2 to the 1j. So 2 to the j is given like that. Then you can find out the number. Why it is 0.769 plus j 0.6389, something like that. So this is complex part and real part. Why these numbers comes out? How to find out? That is the real questions. You try to understand how to calculate this one. I said that any complex exponent are related to sinusoidal functions. Okay, and the same thing can be, you can use Excel. In case of Excel, the complex number can be accessed by use of prefix im, imaginary. Okay, so you would like to calculate this one, imaginary, SQLT and 1j. Okay, this is better. Complex number defined by real part is 0, imaginary part is 1. This is I. This is complex number. Okay. Then I would like to know that the im square root j a1. So I would like to calculate this one. You can see here 0.707 plus 0.707 I. Okay, this is imaginary part and this one is real part, like that. This is the same as im exponential. The a1 Okay, complex. Real part is 0, imaginary part the pi over 4. Okay, this is e to the j theta. In this case, theta is a pi over 4. That's the same of this one. Okay, you can do this one. So Euler equation can be implemented in this way: exponential function, but this number is imaginary, the complex number. That's why I attach im in front of these exponential functions. Anyway, you can try to calculate this one by use of Python or Excel. You can try to calculate, but the calculation, more important thing is to understand how to handle the complex exponent. Okay, go back to the exponential function here again. When you handle the exponential function, you need to keep in mind that this phrase. This says that any exponent value, then the x is the exponent. We can express these things as this way. Okay, this x should be unitless. Exponent is x at here. The x should be unitless number. What is the unit? Unit provide meaning to the number. Okay, for example, here is a 3.2. Okay, this is just number. If I attach unit sec, then this 3.2 means 3.2 time sec. If I change the unit kilogram, then 3.2 means a mass of the mass, so it's 3.2 kilograms. We can change that one. If I change that one 3.2 meter, that is length. Okay, so unit is important because it provides meaning to the number. But the any exponent like this one should be unitless. Unit cannot be existed here. Think about why this requirement are important. All the exponents should be unitless. To be a unitless number, it should be ratio or normalized. Okay, so do not try to memorize this one, but try to understand why. And I said that the complex exponential terms are sinusoidal one. In case of sinusoidal, we are using radian angle. So what is the radian angle? Radian angle actually a ratio. Okay, this is ratio. That's why it can be used as an exponent. Think about the radian definitions. It is a ratio between length of arc to the radius. That ratio is defined as radian angle. Okay, so keep in mind radian angle is just the ratio between the length of arc to the radius. Okay, now move on our main topic. So the complex exponential functions. So complex exponential are shown here. This figure shows that the unit circle, okay, the radius is 1. Here is angle equals to theta. Then this point can be expressed in the polar form. Magnitude is 1, angle is theta. This the same polar coordinate can be expressed as 1 times e to the j theta. By use of Euler equations, real axis is cosine theta, but the imaginary is sine theta. So here is this is cosine theta. This real axis is cosine theta, but the height, the imaginary value is j sine theta. So this is the Euler equations. Then by use of Euler equation, we can define complex sinusoidal functions. Here e to the j omega 0 t. Sinusoidal function is a periodic one. So let's assume that the period of the sinusoidal signal is t0. So xt plus t0 are equals to xt because t0 is the period of the signal. So here shows the sinusoidal signal characteristics. The sinusoidal can be characterized by the period of t0 and amplitude a, and offset phase due to the time delay. This is td. Here shows the signal expression. A is the amplitude of a sinusoidal signal, and omega 0 is the angular frequency. Is defined by 2 pi over t0. t0 is the period of the sinusoidal signal, and plus phi. Phi is the initial offset. It means at t equals 0, cosine phi is the initial phase. So the initial phase is phi, but this one in fact related to time delay td. So we talk about the time shift. That's this factor. Let me give you an example. Here is Excel files. So I would like to gamma is consisted of alpha and beta. So okay, this is alpha and beta. Let the alpha equals to at this moment 0.0, and image the beta terms are 2 pi. Okay, beta is 2 pi. So gamma is complex number, alpha is real terms, beta is imaginary terms. So at this moment it's real term is 0, so I would like to apply some number. Okay, let us assume that it's 0.5. Then this is the real term is 0.5, imaginary term is 6.2j. Okay, and I would like to plot that signal from time equals -2 and time step about 0.2, 0.2, 0.1, okay, 0.1, and then you can add that one. Okay, make a constant. So I would like to from -2 to +2. Okay, it's 47. Okay, I would like to plot exponential gamma t. Okay, let that is g times t. This one is gamma g. Then I can calculate that one. I am exponential. I am product. Complex number is this one and multiplied by this one. But this number should be constant. This number should be constant. Okay. Okay. Then gamma times t. So I assign this as a time variable. So this is complex number, and this is it. So I calculate the complex sinusoidals here, and to figure out that expression, I do this one into this way. At this moment, I calculate exponential t gamma. Okay, this can be expressed. Okay, to the alpha t times e to the say beta t. So it can be expressed e to the a t, see that, cosine beta t, plus j e to the a t, see that, sine beta t. Okay, this is the terms. So at here the real term corresponds to e to the a t cosine beta t. Imaginary term equals to e to the a t times sine beta t. So I would like to separate the real and imaginary component. For real component and imaginary component. Here I am real component of this one. I'll collect here, and imaginary component. Select here. You can see here that the point 367 is a real term of this one. Imaginary term is 1027 times 10 to the minus 14 is the imaginary terms. I repeat that one. So I find out, I make it hide. So this is real and imaginary terms. I would like to plot real and imaginary term along the time. So to do that, I try to plot that one. Okay, let's try this one, and select data. Okay, this is a name and x variable from here 47. I would like to plot real term here 47. Okay, this is real terms, and I would like to add another one. It's imaginary terms. X changing from -2 today to it's a 47, and imaginary terms is this one 47. I plotted two graphs. One is the real terms, another one is image term. You know that blue one is real terms, the orange one is imaginary terms. Real term is real term follows the cosine signal. You can see here real term follows the cosine. So at time t equals 0, it has some value. T equals 0, it has value. But the imaginary term follows the sine curve. So at t equals 0, it should be 0. So the orange one passing the origin at t equals 0, it should be 0. Okay. And if I change the alpha or beta value, shrink this one, and I would like to increase these terms, then what's going to happen? Okay, I changed this 1.0. So what happened? The rapidly increasing. Okay, but what about changing -0.5? Then it's decaying signals. So you can feel that what's the function of this 0.5? It's increasing. But if I take -0.5 for the alpha, it is decreasing. And the beta terms control the alternating speed. If I increase this one about 2 times faster, then you can see much faster. But the curve amplitude follows the same curve. The amplitude controlled by the alpha, but the frequency is controlled by beta. Okay? If alpha is 0, it's a sinusoidal one, as we expected in the Euler Equations. Okay? Okay, so beta controls the frequency, the alpha controls the amplitude. If alpha equals to 0, it means that this term is 1. Alpha equals 0, then this goes to 1, this goes to 1. Okay. So we investigated the complex exponential function. The complex exponential function is actually sinusoidal function. Here shows the exponential function, how we gonna view that one. Exponential j omega t is the cosine omega t plus j sine omega t. So this is real term, and this one is imaginary axis, and this is over time. Then starting from t equals 0, the cosine equals to cosine 0 is 1, sine 0 is 0. So at t equals 0, this e to the j omega t are equals to 1. So that's this point. Imaginary term was 0. As the time goes on, the cosine terms is decreasing, but the imaginary terms are increasing as the time move on. So it goes like that spiral. So if you take real terms of the exponential one, that gives the cosine terms. So at the cosine term has the unit at the t equals 0. This is t equals 0 and t increasing. But if we taking the imaginary component of the exponential one, then that gives a sinusoidal sine wave. Sine wave at t equals 0, it is 0. Imaginary term was initially 0. Okay, so as time goes on, imaginary terms alternating along the sine curve. Okay, you see the discrete exponential signal here. Here shows that the exponential j omega 0 times n is the index number. It's a sequence. Okay, this one is the discrete exponential signal, and as the Euler equation says that it is equals to cosine omega 0 times n plus j sine omega 0 times n. In this sinusoidal signal, we assume that the period is n. Okay, then it should be satisfy these conditions. Exponential omega 0 times n plus capital N should be equals to omega j omega 0 times n. This is definition of the period. So n becomes the period. To be the period for the n, it should satisfy these conditions. Exponential j omega 0 times large capital N should be equals to 1. So it means the 1 is corresponding angle is 2 pi times integer multiple. Okay, so omega 0 times n should be 2 pi times integer multiple to satisfy these conditions. This condition means that the periodic condition of this one. So in these equations, if dividing n to the right hand side, then left hand side, this is typo, so that I would like to correct that one. Actually, this one should be omega 0 over 2 pi. Okay, so the m over n should be equals to omega 0 over 2 pi. So we would like to calculate with respect to n. So n is equals to m times omega 0 over 2 pi. So this is correct. Okay, n should satisfy these conditions. Okay, and also the m and n didn't have any common factor. Okay, this one is discrete exponential signal.